much better than I do. And machine learning is something new to me. And the reason I got into this is because it looks like when I first look at this thing, it seems like very much related to what uh, the kind of research I've done over the last 4 decades, and mainly finite element and multigrid. So today I'm going to talk about my approach to deep learning, some aspect of it through something I know very well, like a finite element and multigrid. Hopefully give a little bit of different perspective about how the deep neural network, deep learning works. Wait a minute, what happens? Anyway, I want to give some very preliminary introduction to get the language in, in place. And anyway, when talking about machine learning these days, one of the main things that it look image classification. For example, how do you I could tell the difference of these three species? And mathematically, we use supervised learning. So the idea is that you have you take you know um, the different images and you do the label image. You want to mathematically, I would call it, you treat each image as some kind of, suppose you have a 3 million pixel, say, image. You can treat this as a point in 3 million Euclidean space. So the mathematically to oversimplify it is to find a function from RD in this particular three classes case. 3 million kind of D is 3 million, for example, to R3, such that you do the matching, do the interpolation. If it's a cat, you do 100. If it's a dog, 0100. And when your new image come in, so you can you just make the prediction. And so this is the one of the so how do you do these things? So let's say in the statistic, you look at the linear models, and when you say this is a binary classification, and so you can put a hyperplane in between, just like all the statistical course teachers. You do non-linear separability, but this one is more or less, you know, it has the outliers, it's still linear separable, but this one is not not linear separable. And but the first thing is when I was studying this thing, so we need to you have the binary classification to kind of a multi sets, linear separable sets. Actually, and mathematically, the way to generalize the multi class kind of separability somehow it's not commonly studied taught in the statistical courses which textbook I was looking for. I just want to mention a little bit here. You're looking for K hyperplanes such that you take in the class AI, the hyperplane has the largest value. And for example, you have three classes of sets here. If you take the one plane is kind of A1 is the bigger one here, the biggest there. So you have three linear functions. And so when you have a binary case that you only have one hyperplane, but in this definition you have two hyperplanes, you take the difference of the two. That's how you do the generalization. So anyway, you have, you know, you can also do this standard technique. Maybe in this case, for example, you maximize the likelihood functions, and I'm sure everybody in this audience knows. But mathematically, I was, you know, you can prove that if idealistically the original K sets are linearly separable, and if you put a regularization function here, so If lambda is sufficiently small, and the regularized problem, the logistic regression, which is strictly convex, you can do, that's the separation of the job. You're able to separate. Basically, when you suppose in the idealistic situation that if the linears, if all the given data are linearly separable, just mathematically speaking, you can actually use the logistic regression, and even without, you can still get the separation. But if you don't have the regularization term, actually you do not have a global minimal. But if you do a regularization, you have a unique global minimal to classify the images. Anyway, to classify the sets. Now, of course, this dog and cats and the rabbits are not linearly separable. And the nonlinear model is that we call this nonlinear separable. You find a mapping, which you may call the feature extraction, to map the image 5D to make hopefully a lower dimensional space, such that the image of the sets are linearly separable. And of course, in practice, it's not 100% linearly separable. You have a certain probability that is true. And of course, a trivial example, for example, is that this is not linearly separable. You find a nonlinear function, so it's become linearly separable. And like this image which I showed earlier, you have a dog and a cat and rabbit. So what kind of image, what kind of linear function you can get? First of all, we need to get a nonlinear model. So then you put the nonlinear model, which is the image, the map, the image will become linearly separable. Then you do the certain linearization, you become this kind of empirical kind of loss function. You somehow find the minimizer of this function. And in practice, you say this is how to formulate the learning. So you have the data, labeled data. We're looking for this nonlinear functional class, which I kind of show you is a logistic regression composed with this feature map. You minimize these problems, and once you get a minimizer somehow by some training algorithm. So suppose you give you another image. This is what we call generalization, inference, or whatever. You give me a new image. If I get this probability distribution like that, let me just say, because you have 70% of the chance that the image is in the first class, that's a cat. I suppose this is kind of a quick description how from mathematical kind of viewpoints, how the machine learning is done. Now, one of the basic, there are many questions can be asked about these approaches. And what is a good functional class for this nonlinear kind of feature mapping? And what will be a good model? Even you have the functional class, you have how to make use of it. And what is a good training algorithm? And this training algorithm, of course, it involves, you want to reduce the good training error fast enough, and more importantly, you have to have very good generalization accuracy. So my approach is, I've been working on finite element method, a multi-grid method. So I'm going to use what I know to look into this problems. And you can still hear me, right?
Yes, we can hear you.
Okay. Now I'm going to talk about finite element. Okay, my favorite. Before I do that, of course, everybody knows that, for example, you could do polynomials. Let's say polynomials is one of the probably the first functional class you use, but one of the problem here is of curse of dimensionality, which I'm sure most of you know. But my favorite functional class for my research for solving partial differential equation or finite piecewise polynomials, what we call the finite element. And so let's say we're talking about piecewise linear function, for example. You give a domain, you do some sub-interval, you do a globally continuous for piecewise linear functions. This is a finite element. Piecewise polynomial of degree 1. You can quadratic, cubic, you can do that, but it's linear. So you can generalize this 1D, 2D, 2D would be a triangle, 3D or tetrahedron. You have all this partition of them, we call it a grid. And 1D is an interval, 2D is a triangle, 3D or tetrahedron. And you put the piecewise linear on it. That's the kind of the finite element space I've been working on. Now, how let's take a little bit closer look at this function class. So you take this is like a special linear functions, a piecewise linear function, and this is between 0 and 1. And so it turns out you can, for the piecewise linear function in the previous page, you can have a basis by generated by this phi, this between 0 and 1, do a dilation and scaling, for example, you can WH equal to that. You can get, these are the basis function. It turns out these are the basis function. This is like to represent any linear piecewise linear function can be written as a linear combination of this phi I. But if you do the machine learning, one of the most popular activation function is ReLU. ReLU is x equal to less equal to 0 is 0, x greater than 1 is equal to x, is a max. And it turns out this activation function, this hat function, what I call a hat function, can be written as a combination of this the positive phi in this way. So by saying that this activation function, this basis function can be written as the span of the ReLU, if you take the W and B in arbitrary. So what that tells me? So this is actually, if this is the span here, the one here, it is the one-dimensional neural network with ReLU as activation function, one hidden layer. This tells me that finite element is a piecewise, it is contained in this ReLU neural network. What you call a DNA one level, and the example is that F is in here, it can be written as a linear combination of that. And the deep neural network activation function ReLU is we call what in machine learning call this one called neurons. Generalization to multi-dimension for the ReLU is straightforward. So you replace this linear function inside by the multi-linear functions, okay? In this case, hyperplane. So you get a ReLU in multi-dimension. This is with one hidden layer. This is a neural network function. But you can also do replace this ReLU by arbitrary activation function. You can do multi-layer. So you begin with linear functions. You do the activation component-wise, and you do another linear. You do activation again. So this is what we call the deep neural network. So you do again linear component-wise activation. Activation sigma is a one-dimensional scalar function. You can do ReLU, and you do linear again, activation again. So you depend on how many layers you do, you get a deeper and deeper. You get a deeper neural network, we call it DNNL. And so now let's talk like what the ReLU look like. ReLU is it's very easy to say it's a space of continuous piecewise linear function, but it's going to be look like it's not the kind of classical finite element grid I know, but it's kind of intersection of different hyperplanes, and you get this piecewise linear functions. one of the first questions when I actually look at the things, the first question I was asking is that how do you compare this crazy looking piecewise linear function with something I know very well? For example, you a priori given a grid, all right, which is kind of triangles, maybe locally refined. These are piecewise linear. How these are related? Another way to say is that, for example, if you do this, the left picture, you can divide these polygons in each of the subdomains. You can make it into a piecewise linear function like a finite element. So it's in general, the DNN is some kind of a linear function, piecewise finite element functions in some kind of very crazy, very special kind of grid. The grid is not given a priori, but it's given by all these different weights. Now, what's interesting to me is that if you can, for given finite element grid like that, can you write this finite element function as your redo neural network functions? So it turns out in 1D is certainly true. It's very easy to see. 1D, any finite element can be written as a DN, which I pretty much explained earlier. It turns out for D greater equal to 2, if we only have one hidden layer, we have proved you cannot do that. It's not so difficult to see that because the grid is very, very special. But we can rigorously prove it cannot be done. But if we increase the number of layers, it turns out this can be done. So it's so finite element can be recovered by deep neural network, real deep neural network. So ReLU DNN is the most commonly used, the dominantly used in machine learning, this the deep learning. It turns out it's exactly as a set of functions, it's really exactly the piecewise linear finite element that which I'm familiar with. So one of the first messages I'm sharing here is that the so-called ReLU DNN, which is most commonly used neural network, as a function class is exactly piecewise linear finite element, which we have been using for years for solving partial differential equations. But you can actually, you can actually replace to raise the power of k, for example. Well, piecewise linear function, I'm going to raise the power of k of the ReLU. I call it ReLU to the k's power. If you put them together, you can generalize very easily to. So the interesting thing is that if you raise the power of k, you get a piecewise polynomial of degree k. That's also kind of finite element. But another thing which is interesting is that it gets the corresponding smoothness. So if you have k's power, it's going to be the hk in the Sobolev spaces. Interesting enough, I've been working on this problem for many years. There's an open problem in finite element method. How to construct a finite element space as a subspace of HM for any n and any dimension. Namely, the difference here is that you have the given a grid a priori. On that grid, can you construct a piecewise polynomial that can be as smooth as you wish in the global domain? It turns out this is an open problem. And I worked on this for some time, but we still don't know how to solve this problem. But now, if you use a neural network, the solution is trivial. But you have it's not the difference that the grid is it's not given a priori, it's kind of hidden. So what does it look like? For example, this is the linear, but if you do quadratic, you have this kind of grid. We plot this one. This grid is curved grid, but it's piecewise quadratic on this all these little subdomains. And so we have some very special looking kind of piecewise polynomials, if you think about it like quadratic. Now, what's interesting thing is that in machine learning, of course, one of the important area of research is that what is the representation power of this type of functional class? Do you still have the curse of dimensionality? Things like that. Now, the first question you ask that if you give, suppose you take a general activation function, is this function can approximate any continuous function? Mathematically say, would they, under what kind of sigma this would be dense in the continuous functional class example? It turns out if sigma is polynomial, you cannot do the job because if sigma is polynomial, you still get the polynomial of the same degree. The interesting the case in one of the simple result in the early literature of the neural network, as long as sigma is not a polynomial, you always have the density. You always have the representation power to some degree. So you can use it turns out this activation, this thing is dense in the, if and only if sigma is not a polynomial, which is kind of interesting. But of course, when you actually do this estimate, one of the things is a sampling argument. You can actually prove that if you have n neurons and with some assumption, you can get a larger class of you have this n to the negative half result. This is by looking at this, you can probably reminisce into something like a Monte Carlo type of. It is a it's the way to prove this that you can use the Monte Carlo sampling. Sorry, and the rate of convergence n to the negative half. This is one that actually people argue that this is the rate of convergence does not depend on the dimension. So it's like a Monte Carlo method. It's kind of friendly with high dimensional space. Now we can do more refined analysis. Suppose you do the reduce to the k, and it turns out you can gain a little bit of things. You can gain like a little bit 1 over d out of it, and for the reduce to the k, which is piecewise polynomial of degree k. But when I wrote also some paper with my postdoc Jonathan last year, you can actually, in general, even for the general activation function, you can actually improve that. But anyway, but the most interesting things I want to share right now is something we recently got just a few in the recent weeks, and with Jonathan, my postdoc, you can actually prove that not only, so let's take a thing of m equal to 0, okay, just for thing is L2. Then so it's a negative k plus 1 for L2 now. In the past literature, you have this negative half, or maybe you gain a little bit. But here, as long as the U is sufficiently smooth, this is related to something called a barren space, which I don't have time to explain. You really get this very high order of convergence. And the interesting thing is that it is also optimal. You cannot do better. But if you look at this 15 here, and of course 14 and 15 differ by a logarithm, we can prove the lower bound is m to the, based on one of the work I did a few years ago, I did in the polynomial approximation. This is reference number 1 here. You can prove the lower bound. So if you do ReLU k, the power, you can get where the optimal rate of convergence, somehow the rate of convergence is independent of d. Let's just compare this in the finite element method. Okay, here's a UN is a neural network with n neurons. Okay, with n neurons. So you can think of number of parameters like n. If you do finite element, traditional finite element, you do piecewise polynomial with n elements, you still have n parameters. We can actually prove that 16 is both the lower bound and upper bound. You have to divide this by d. So what does that mean? If I put this together, if you took the neural network, the neural network with n neurons, still piecewise polynomials, and the Vn k finite elements, n parameters, but the finite element. If let's just assume my solution is sufficiently smooth, the U, the rate of converging, you can raise the power of D. So anyway, when I'm telling this result to my finite element colleagues, nobody believes this because this seems to be too good to be true. But I think we can actually mathematically prove that. So this is actually demonstrate that this deep neural network function class, even though they are piecewise polynomial, but they have different structures, but they really have the finite element suffers from the curse of dimensionality. But neural network function class, I would hesitate to say it doesn't suffer the curse of dimensionality because you have all the constant here and there. But I think in the asymptotic rate, it is really kind of dimension friendly, and it's much better. Again, we're dealing with piecewise polynomial about the same order of degree of freedom. But the rate of convergence is significantly higher. When D is larger, it's even better. So that's the my take on neural network function, deep learning, or this nonlinear model from my finite element point of view and the approximation analysis. We're actually working on this with Jonathan, and recently we did a very kind of comprehensive investigation. How should the approximation theory should be carried out for neural network? If anyone is interested in this topic, I can send you some more papers. Now we'll come back to the training algorithm. That's what my take on the functional classes. Now we do the training algorithm. Training algorithm, the main thing is the gradient descent method. The stochastic gradient descent method is the dominating method in the industry. So I want to give some example to have some taste of what this algorithm is doing. Suppose I'm taking a very simplistic problem, quadratic, some kind of optimization problem, which is equivalent to solve. Suppose A is symmetrical positive definite matrix, for example. How do you do the minimization? Now you do the gradient descent method. This is my F. This is kind of this is gradient descent. What eta is called a learning rate. If you do these things, it's really what we call Richardson iteration in the linear algebra. This is something which I know very well, this topic. Now you can do a scaled descent method. In machine learning, you may have something Adam or that kind of method. You do some kind of preconditional scaling. This is like Jacobi method, scaled Jacobi method. So you can relate this to something like Adam method. Now the question is that we can actually prove, for example, if A is symmetrical positive definite, this one converge. Now the question is, what is convergence behavior? If you play with machine learning to actually train this model, for example, ImageNet, I actually have this DGX1 with 8 process GPU. It takes 2 or 3 weeks to finish a training. It takes forever. Well, why is that? So I give you a simplicity, very simple example. I take how I'm doing with my time. Don't you?
I think you can use about 10 to 15 minutes.
Okay, yeah. For some reason I don't have a watch here. Okay, okay, over here. And okay, sorry. So this is kind of my favorite example. You take this problem is like A0 is semi-definite matrix. You have 310 eigenvalues. This one is you have this is in the kernel. Now you do gradient descent method to solve this problem, okay? You do the gradient descent, but when the things you want to watch is that when epsilon equal to, say, you look at the residual less than 10 to the minus 8, epsilon equal to 1 is symmetric positive definite problem. If you do gradient descent method, choose the appropriate eta, I forgot what it is. And you get a 37 iteration. Now the question, when epsilon goes to smaller, and what do you expect? The problem become more singular, and it's getting more iteration of it. So see how bad this gradient descent method is. Even for this extremely simple problems, it takes hundreds of iterations to get a decent accuracy. Huh? One of the interesting things as a mathematician, we ask what epsilon equal to 0? Epsilon equal to 0, I'm choosing the right-hand side, specifically in the range of A0. And in this case, it turns out there's some surprises. You only need a 20 iteration when epsilon equal to 0. There's really a big changes. That this actually leads us to remedy. How do I actually fix the problem, which is more efficient? You know, if you were in the 3 vector, you do the expansion, but I'm actually doing this 4 expansion. E is a singular one. When you do a 3 vector expanded by linear dependent vector, this U1, U2, U3, they are kind of actually non-unique. So you write this any U as this one. So the problem become a 4x4 problems. It's a singular. And I told you earlier, singular is, it doesn't bother me. If I do the gradient descent method with this Jacobi scaled gradient descent method, surprisingly, the rate of convergence is uniform. Haha. This is like, you know, in this machine learning, you have this over parameterization seems to do the job. And from here, I do 3 to 4. I do some kind of more parameter, you get much better convergence. Day and night difference. If this one, you can actually rewrite this as algorithm, what I call a multi-grid method. And since I'm running out of time here, but now I'm coming back to the differential equation. If you think of piecewise linear functions, usually when you do suppose to solve the differential equation, you have this basis function. But I could throw in this cost-based function, which is when it's a linear combination of that. So I'm going to throw this one in as well. So I do the expansion. I kind of over-parameterize. Let me give you an example of for example, multi-grid method for the Poisson equation 2D. So the way to do it is that if you do a gradient descent method, in this case, it is really uniform grid. It's some kind of convolution. It can be written like that. And mathematically, it's like when I solve this equation, traditionally, you just, this is like, this is with 3, you can think about 3 by 3. This is what I call a 7-11 game. Huh? If you have 7 bases, or you have 11 functions, for 3, 4, I don't know, 11, you do the over parameterization with is kind of framed, the kind of linear dependent functions. If you put this into the picture, you kind of solve this problem. This is how the multi-grid works. But mathematically, you can think about do the linear expansion of this 11 function instead of 7 function. This is in comparison instead of 3 functions, 3 bases in terms of 4 vectors. If you do that, you solve this problem. There's a day and night difference. If you do the gradient descent for the original basis function, it's like when you increase the things are going to, the number of iterations of GD increases. But if you do this expanded system, if you do over parameterize it, the multi-grid convergence is uniform. And I just want to show you that in the typical profile of the training algorithm, the first few iterations, the loss function go very rapidly, and it's going to saturate. But the multi-grid is that before you get saturated, because slow down, you rescale the problem, then you multiply the SGD again, gradient descent method. So somehow you have the very fast convergence at the straight line. So what does this has to do? So I have two methods here. One is that there's a potential to speed up the traditional training algorithm. That's one thing. Another one is I'm going to show you that you can also use the multi-grid idea. For those of you who have played with the convolutional neural network, convolutional neural network, you have a image of different resolution. You do the pooling, which is very similar to the multi-grid method. This is how I'm going to how motivated me to design a convolutional neural network by using multi-grid procedure. But look at this slides, please, and as you can see that if I remove the red, the print, the things in red, that's precisely a multi-grid algorithm, a major part of a multi-grid algorithm. So I actually taught deep learning at Penn State, a couple, 2 or 3 times. I actually asked the student, first of all, implement a multi-grid method and get the things to work for PDEs. Then I just asked them to go change this few lines of code. So that's my convolutional neural network. And that's my, the G is the image, somehow this one you kind of increase some channels. And then you do the activation function. This is basically, if you think about image, if you do the reload, basically, when you see a negative pixel value, just make it 0. If you think about pixel values. And after you do some multi-grid iterations, so you do what kind of the feature extraction, which is a multi-grid process. So so that's how I got what I call an MGNet, and that's my kind of CNN. And this is very well structured, and very few hyperparameters to train, to choose. If you compare with the difference in the classical multi-grid method, this A of L, SL are kind of a given a priori. CNN, if you do that, this is MGNet, you have the same structure as a multi-grid, but all these convolution kernels need to be trained by the data. And as I mentioned, the activation in this case, if you really think about a multi-grid algorithm, if I see something negative, I drop it off, make it 0. Of course, the reload, as I explained earlier, it has other reasons to be a good activation function, to have good representation power and all that. The only thing which is different from the traditional multi-grid method, we introduce extra channels. So one of the reasons that this somehow this neural network is getting very big and bigger. On the one hand, we like over parameterization, as I mentioned earlier. On the other hand, somehow people in the deep learning community, you need a lot of parameters so that this thing is generalized well. But on the other hand, if you get a for example, these days you have a transformer, I start looking into these things. You have lots of parameters, train this forever. But actually, the way I say it mathematically, one of the things in my ongoing project, I want to reduce the number of channels. I don't think the number of channels are necessary. And that's I don't want to get into too much detail. So again, this multi-grid and the CNN are very closely related. I was able to make a very tiny little bit of modification of a classical multi-grid method, turning into a CNN. But this is very much related to ResNet, residual neural network. When as I can see from my MGNet, I could extract, somehow get the pre-active, what they call ResNet out of it. It's very closely related. And anyway, I wrote a few papers on these things. I'm running out of the time. I just want to mention about how this one performs. And so if we replace this the Sapphire 10, for example, and Basically, I have the, you use the, I have a fewer parameters, but a higher generalization accuracy. If you compare with this old standard model. And another thing is that this one scales very well. If you actually increase the number of channels, for example, I have very few hyperparameters to tune in this in my model. And if you are willing to increase the number of parameters, I just want to say, okay, increase the channel. The other thing I don't change. So you see from 79, this is 700. You have the 81, 82, you can actually increase the generalization accuracy. It's interesting. It's still a mystery to me that indeed, if you have more parameters, you get a better chance to generalize well. Over parameterization. All right. I just want to. I think that my time is up. Anyway, I said the deep neural network and it's still piecewise polynomial. It's still finite elements, but the way it's given the different structure. And it has what I call dimension-friendly error estimate, or maybe what they call, you don't have much of a curse of dimensionality. The classification problem, the way I look at a machine, this one is that mathematically, I want to think that if I have something non-linear, it's not linear separable, I want to convert it by the feature mapping, so that in this feature space, it's become more or less linear separable with high probability. So I combine the logistic regression together with the nonlinear feature mapping. This nonlinear feature mapping can be given by the deep neural network. In particular, kind of what I given by the multigrid. I will make a very little change, very few changes of my code. I get a more efficient neural network. But I worked on multigrid in the last 4 decades. There's lots of mathematical, very rich mathematical theories in it. And I thought this might be give me a good chance to understand why say in works. We can provide some mathematical theories. And somehow you have some mathematical insight to this one. But because of the simple structure of my MGNet, I believe that there's a chance to get a very small, what I call steamer CNN with higher generalization accuracy. And the things I really kind of deep deal in my heart, I really want to work on is to speed up this training algorithms. This is something I'm working very hard on. I think I'm running out of time. For that, I'm going to stop here. Thank you very, very much for your attention. Thank you.
Thank you very much for your very interesting talk. If there is any question from audience, please unmute yourself and please feel free to ask question to Dr. Xu.
Hi, Jinchao. Thank you for the interesting talk.
Thank you.
I have a question about the first part of your talk. So
yeah,
you have a ReLU raised to power k, right?
Yeah.
So how does that when you calculate it, is it hard to optimize it? So when you do the stochastic gradient descent, is there a problem when you try to estimate the parameter numerically?
Algorithmically, there's no problem superficially. Okay, now it's quite you tune these things.
Yeah.
And the way I see deep learning is everything is in the training. The structure of the network is just make it a little bit easier to train to get a better generalization accuracy. And I have not got around to answer to your question. I don't know. And this is something very new. And but to answer your question in a different way, I don't really even like ReLU. I have evidence. ReLU is everybody uses ReLU. I recently did some work. Somehow have some strong evidence saying that we should not use ReLU. If I what I said is true, that is very much against the entire industry. So I should not say that probably before I can get some more details. But the ReLU is very peculiar functions. But if I think about it in terms of finite element, anyway, again, the Trainian ReLU, by the efforts of all this industry, people accumulate a lot of experience how you tune these parameters. And so in some simplified situation, I seem to be able to use ReLU and actually ReLU square to do a better job. But I'm not in a position to say how this is going to work in general. But this function is indeed smoother, much smoother than the ReLU. If somebody think about a high order method, even though this way you can take more derivatives, approximation is better. If you're asking me just mathematically, because the things I cannot answer is this generalization accuracy. If you think about just a Trainian accuracy, I can probably say, it's as easy as or maybe even easier than the other one. But generalization accuracy is something which we have not got around to testing extensively. Sorry, I couldn't really answer your question better than that. It's a critically important question you're asking.
Thank you, Jinchao.
Is there any other question from the audience? So I find it very interesting. So it's really interesting that that for the last the classification problem, you use like smaller number of parameters, but still like you got a better accuracy. I think you got like 2 million like less parameters to get a better accuracy, which was
right. But it's not much. It's like 1%. Somehow, it's like 1%.
But I mean, it's the baseline accuracy is, I assume that this is a generalization accuracy. So the baseline.
This is a generalization accuracy. That's the rule of the game. So
yeah.
generalization accuracy. But for some crazy reason, recently I realized if you want to reduce the training accuracy, it's really easy. But generalization accuracy, no, if you want to increase the training accuracy, is relatively easy. It's quite much easier, but we're talking about generalization accuracy only here, indeed, yes. But yeah.
So for this one, did you use the higher order ReLU?
Or is that just standard ReLU?
Standard ReLU.
So
if you try the higher order ReLU, would it get better or?
Actually, that's a very good question. My understanding of neural net deep learning these days is that this representation power, if you do ReLU square, seems to be better than ReLU. But this classification self-attain specific, the bar is very low. It's very easy to classify. If you think about that, it's very easy to reduce the training accuracy. That's the approximation problem. That's representation. Representation is rather easy. And it is the generalization that is kind of difficult. And if you increase the ReLU, I suppose the power of the ReLU, you get a better representation power. Though despite all this, many people, including myself,
Hi, Dr. Xu, I think your video is frozen and your voice. Maybe the speaker has some connection problem. So maybe we can wait a few minutes. But I think it's also kind of reaching the end of the seminar. So maybe can say that thank you let's thank to the speaker, and hopefully he can I guess he's out. So thank you very much for joining today's seminar. And I hope that all of you have a very nice. Oh, I think he's back. Hi. So yeah, we wanted to thank you for the wonderful talk, and then yeah, I appreciate you coming today and then giving us a talk. And I was hoping that everybody has a nice weekend. And yeah, please, we were hearing about the generalization, and then the better representation power of the value with a higher order. But I think your answer was like stopped hot there.
Yeah, so if you ask me to guess that I have a few comments. The reduced K probably will do equally good job, and but that's what I would guess. The training that you just have to train differently. The problem about from when you change the activation function, then you don't have the a priori knowledge built by all this community. And when I got my students to train this thing, they often use the same hyperparameter from other people. Then my machine is very slow. I have even though this machine, but if you take in order to be credible, you have to use Cepha 10 or 700 at least. ImageNet, for example, is a nightmare for us. It takes forever to train. And if you want to change one set of parameters, you wait 3 more weeks. So it's kind of so it's very slow progress. But again, I think that there's a lots of potential there. Secondly, and I'm actually recently kind of question why we even should redo in the first place. But again, that's a wild kind of. If one of my observation can be generalized to other cases, then we probably have something quite different to say about machine learning. But anyway, the quick answer is that I don't know. We do not have results right now, but something interesting to investigate.
Yeah, it's thanks. Yeah, I was always curious because it seemed like for the better representation, like not ReLU, but like other smooth like activation functions such as the sigmoid, I always thought they would be like, it's easier to work with, but people use ReLU and then it has like a very somehow good performance over the generalization. And my understanding is in general, it's like much harder to capture the like generalization error based on these the different activation functions and different function classes. And since you're said that you are thinking about different activation function, like can you comment on like what makes it like a good activation function or like good function class to work with for these kind of problems?
So the ReLU, for example, in the activation function, the ReLU by itself, as a functional class, the piecewise polynomial, is the basis function you use. Where do you start that one? Different scaling, all that kind of things. I think the whole business of machine, what I do is a multi-scale. You have to somehow have different scale. The ReLU is very good to capture low frequency feature. I believe right now the machine learning people these days only capturing the low frequency of the features, the global features. And if you want to do local features, suppose I have this watch, it's very tiny little things here in you want to capture that. I don't think ReLU is very efficient. That's my guess, because ReLU is more global kind of functions. And again, everything has to do with the representation power. If you think about the activation function, can be the same, but it's the training process can be quite different. And there's something people call even they call the frequency bias. And I think people even like Benjo wrote a paper recently, and he called he called frequency bias. See, if you want to do some people call it a frequency principle. When you do the training of the ReLU, it tends to capture the low frequency more efficiently than the high frequency. And I actually look at this things. I use a different function. For example, Benjo's paper, I outperform his algorithm by a few order of magnitude. It takes forever to converge. I take a few iterations to converge for the model in his paper. So again, I don't know how much general I can, but at least you know, you get his same numerical data. I just use my different algorithm. I get a few order of magnitude better, but that's just isolated example. But it actually means that it has quite a bit of potential if you think it mathematically. Many of my computer science friends say the CNN is a done deal. Wow, they're changing their mind right now because they're doing something like a transformer. Something, but but I think mathematically there are many unanswered questions why people you have to do something like that. And so I'm just questioning pretty much everything what people do from a mathematical point of view. And so I can gain some insight, but the generalization accuracy again, I could offer some explanation from my multigrid. The over-parameterization certainly help you to train much better in the multigrid setting. But if you now introduce the nonlinear activation function, I could not quite generalize my theory into nonlinear problems. But it's something we're working on. Yeah.
Mm-hmm.
There are all the things about training. That's what I think. Yeah.
Mm-hmm. Yeah, thanks very much for your comment. And yeah, again, thanks very much for the interesting talk. I really
my
enjoyed
biased
that.
opinion. Thank you very much again for listening. Thanks for giving me, inviting me to give the talk. Thank you very much.
Thank you. Yeah, I hope that we all see in person someday, and I hope all of you have a nice weekend.
Okay, then. Bye.
Bye.
Yeah, bye, Jinchao.
Bye. Bye.
Yeah.